Hello there, Mr. Mechnick, for a little podcast on laws, theories, hypotheses, and throw in beliefs right away. So today, I would just want to make sure that we're all clear on what the difference between a hypothesis and a theory is versus a law and something that we just believe to be true. So today, there's one major misconception I want to really try to clear up, and this is the misconception is that when scientists come up with these hypotheses and it tests over and over again to be true, sometimes people think that a hypothesis turns into a theory and then a theory will eventually graduate and become a law. Well, that's not how it works. Science doesn't work that way. Theories don't graduate into laws, and laws don't get downgraded if they're disproven to become theories. What we need to understand is how science works. So here we go. First thing, laws are things that are factual. They explain in concise terms any action or set of actions. These are typically represented by mathematical equations. They typically are, and they're always accepted to be universal truths. They don't change. So there's many laws that some of you probably are familiar with. The law of gravity, for instance. It's observable, it's factual, it happens no matter where you are in this universe. So there's many other laws that you probably have come across in your years of scientific studies. So I know Science 9 covers laws of motion. So many of you probably remember those laws of motion or the laws of thermodynamic, the gas laws of conservation of mass and energy, Hooke's law of elasticity, Galileo's law of free fall, Kepler's laws of planetary motions, Newton's laws of gravity. These are laws that happen everywhere in the universe. They are universal truths, and many of these are represented with mathematical equations. So when we look at laws, we have to make sure that we follow the universal form. So if in all cases, when a condition of kind A are realized, then conditions of kind B are realized as well. This means laws are suited to mathematical formulas. So when one condition happens, the result can be predicted. So if something goes up, it must come down. That's a universal law. The law of gravity describes that. So some laws can't be expressed with mathematics, but they're a good guide to classifying laws as statements of absolute truth. So example, Newton's third law simply says, for every action there's an opposite and equal reaction. This can be expressed by force of 12 newtons being applied in one direction is equal to a force being applied in 12 newtons in the opposite direction. So this is again a representation of that law, and it can be very easily represented with quantities. So once we observe the world around us and we understand some of these governing laws of the universe, scientists ask questions about these laws and we can test different variables against them. So scientists design investigations and we develop testable hypotheses. So when we write hypotheses in science class, we need to always make sure that it's a statement that's a prediction based upon observations that you have made, based upon background research that you have done. So the purpose of a hypothesis is to organize your experiment. The first thing you have to do is come up with a question based upon observations, things that you are wondering about. So if we carefully make the hypothesis, we can then move on to the next step of the scientific process. Hypotheses have to be testable. So if we predict the temperature of a gas is increased, then the volume will decrease. We could easily test that. If the length of a pendulum increases, then the period of the swing will decrease. If a runner drinks water and run in a race, then they will run faster than runners who drink a sports drink. This is again a testable hypothesis. So we need to make sure using the if-then format, that's going to be a great way to formulate a hypothesis. But not all if-then statements are good hypotheses because they're not testable. So if you warm yeast, then more gas will be produced. Is a prediction. It's not a hypothesis. If you have not answered the question, what's being tested, what is related to what, is the temperature a variable, is yeast a variable, Is gas production a variable? We need to answer those questions, and that's why identifying those variables, the independent and dependent variables, in the hypothesis statement and saying how one will affect the other is necessary in a really good hypothesis. So when we look at a hypothesis and we want to say, okay, how do we make a difference between the hypothesis statement and a theory statement or even a belief? So the hypothesis statement has to be a tentative explanation based upon this idea, based upon your background information of how things work, the governing laws of this universe, and it will guide you to the answer if you put the hypothesis together correctly. So if a trip was made to the moon, then it would be found that the moon is made of cheese. Is this a good hypothesis? Could we test this? Well, you could construct a rocket to go to the moon and return with samples, make a cheese pizza substituting the moon samples for the cheese, ask people to eat the pizza and see if they can tell any difference from the pizza made with real cheese. Most likely the conclusion would be, hey, this pizza tastes like dirt. This is something that's still testable. It's a prediction that could be tested. It's a little far out there, but nonetheless, it's still a testable hypothesis. So when we look at scientific theories, we sometimes use the term theory in replace of hypothesis when we shouldn't. So some people say, I have a theory. Well, no, you don't have a theory. You have a hypothesis, or you are making a prediction that is really not substantiated by anything. So theories sometimes are controversial because people don't understand what it means to have a scientific theory. And just to let you know, much of what we learn in biology class, much of what we learn in science class is based upon scientific theory. It's usually a really good explanation. So when we hear the term theory, we're not just saying, oh, it's just a theory, or it's made up from this one guy made up this theory to explain something. No, a theory is the best, the most elaborate form of consistent scientific knowledge that hasn't been disproved. Science uses theories to explain things. A theory can never be proved. It can be disproved by experimentation, but theories are well supported by not just a few individuals, but it's agreed upon in the scientific community. A statement that cannot be disproved by experiment may still be highly respectable, but it's simply not part of experimental science. So all of the theories are well documented and proved beyond reasonable doubt. So in biology, the theory of evolution is a major theory that explains how life exists on this planet today. The theory of relativity, the atomic theory, the quantum theory, all of these theories are explanative. They explain something. So a theory is an explanation based upon countless experiments and observations that have been tested over and over again. A single scientist does not create a theory. The theory of evolution was not created by Charles Darwin. It has been built upon. He laid the groundwork for this theory, and we have lots and lots of supporting evidence for it. So the biggest difference to remember between a law and a theory is theories are much more complex. There's so much more to a theory than there is to a law. So a law governs a single action, and theories explain things. They explain phenomena, why things happen. So if you want to use this analogy to help this, keep it straight in your mind, a scientific law is like a slingshot. You pull the cord back to release the rock, and when you do this and you let go, the rock will fly out in a predictable manner. The further you pull it back, the further the rock flies. Those are based upon laws of physics. Whereas if we want to think of this car and all of the moving parts working together to perform a specific task, and that's moving from one point to another, that's a lot of machinery that's working together to perform that task. And so sometimes we can look at making improvements to cars to make them faster, to make them more fuel efficient, to make them lighter, to make them more aerodynamic. But all of these improvements still help develop that car to perform its job. So a theory is very much like an automobile. All of these different parts work together. We can improve on it over time. We learn more about it. We can try to make them better. And if we find out that, hey, maybe this spoiler on this car does in fact make it go slower, well, maybe we don't add spoilers to cars anymore. So nonetheless, theories are explanative and laws are based upon fact. So when we draw conclusions based upon observations, based upon beliefs, sometimes our beliefs will guide our actions because they're based on history. They're not based on anything besides thinking a thing is so. Is this science? No. We have belief systems, which is perfectly fine. But we also have to remember science answers questions using a system to do so. You can believe anything you want, but those beliefs are based upon your feelings, based upon what maybe someone has told you. You may believe that all dogs are friendly, and this might prompt you to pet any and all dogs you see. But I'll tell you right now, not all dogs are friendly. So your belief may be based upon your past, your experiences, your family, your religion, your habits, but not all of your beliefs are scientific. The result, no conclusions can be drawn from what you believe. Conclusions are drawn based upon science. We use science to explain things. We use the laws in the universe to help us understand these theories. I hope this presentation has helped you understand the difference between law, theory, hypothesis, and a belief. We'll do some practice with this tomorrow because it's difficult to distinguish sometimes between beliefs and theories and hypothesis.